Swayam Prabha. Digital India. Educated India.
Now, we talked about the energy flow diagram and we talked about the overall global energy use. We would like to see how does India compare with the world and what are the expected growth rates in the Indian context. So, what I suggested to you that you should actually look at different countries and try to do the energy balance. We can do the same thing for India. We have a table which gives you the indigenous, what is the amount of production of coal, oil, natural gas, what are the imports, exports and the stock changes, and then you can get the primary commodities. Some of them are being transformed into secondary commodities. For instance, coal is being transformed to electricity, and even in electricity we are importing and exporting. We are importing electricity from Nepal and we may be exporting again to some of our neighbors. Then maybe stock changes and then there is a final use. So, this is what is there. There is in the International Energy Agency there is an energy statistics manual, and with that you can look at the database and you can actually work out this for any country that you want, and that will give you also a sense of the calculation, a sense of these energy flow diagrams and a relative sense of magnitudes. Is how important is hydro, how important is coal, how much of the energy is imported for that country, and I would encourage you to do this on your own so that you get a sense of the overall energy. So, when we talk about the energy balance, you will find, for instance, if you are trying to do this for India, we would like to see in a year how much coal are we using, how much oil, tons of coal or barrels of oil, and then in the case of natural gas, it's often expressed as normal meter cubed or standard meter cube. Electricity will be in kilowatt hour or million units, and then for a certain amount of coal, we'll measure the energy content by either the gross calorific value or the higher heating value or the net calorific value based on the fuel composition, and then we can convert it also into coal equivalent, oil equivalent, that kind of thing. So, typically when you look at an Indian balance, we take Indian coal has an average energy content which is lower than that of international South African or Australian coal, and it's right now the average may be of the order of little less than 5,000 kilocalories per kg, 4,500. You multiply that by 4.18 kilojoules and you get 18.8 megajoules per kg. And oil has a greater calorific value per kg, it's about 41.8 megajoules per kg, and natural gas is of that same order of magnitude. In the case of nuclear and hydro, it is very difficult to talk about the amount of flow of water, but what we know is we know the generation from hydro plants, and we work backwards using the efficiency. So, a hydro efficiency plant efficiency is of the order of 85%, nuclear of 25%, and then you can get what is the energy content. So, some of the terms that we may want to look at when we do these overall balances, one is the plant load factor. Plant load factor of a plant is the actual generation of a plant over a period, which may be a day or a month or a year, divided by the maximum possible generation if it is operated continuously at the rated or the design value. So, typically what happens in these plants is that the plant would like to operate at high plant load factor. Why is that? That is because whatever investment you have, you would like to recover it over a larger number of units. So, your electricity would be cheaper if you have higher plant load factors, but the plant load factor will be dictated by the fact that you cannot just supply electricity to the grid, there has to be a demand for that electricity. So that supply demand matching is one of the factors when you look at the electricity system. But so plant load factor is one of the things. In every power plant, there is an auxiliary consumption. That means in a coal based power plant, you will find that there are fans and there are pumps, and these consume electricity. So of the electricity which is being generated, some part is being used internally inside the plant itself. That is the auxiliary consumption. And so what we often do is we can specify the output of a power plant in terms of the gross power output or the net power output. In the Indian power system, we specify it usually by the gross power output. In the Europeans and US often talk about it in terms of net power output. And then the gross power output minus whatever is being used internally becomes the net power. So the auxiliary consumption percentage is the auxiliary consumption into 100 divided by the net power output. So if you look at these terms, let's do a simple calculation. So if we look at a thermal power plant which is rated at 500 megawatt gross, it has 9% auxiliary consumption and has an annual PLF of 80%. So we want to calculate the annual generation in megawatt hours and in million units and in gigajoules. And the next part of the question is, if the plant has an efficiency of 38%, calculate the input energy supplied to the plant. We can do this in terms of megajoules, petajoules, terajoules, in joules basically. And if the input energy used is coal, calculate the amount of coal used. Okay, so let us solve this problem. Let's look at, this is a 500 megawatt plant, right? And 500 megawatt, this is a unit of power. So if we look at 500 megawatts in an hour, the plant generates, if it's operating at its rated load, it will generate 500 megawatt hours. In a day, it will generate 500 into 24. And in a year, the maximum that it can generate if operating at its rated load is 500 into 24 into 365 megawatt hour. Now this turns out to be, you can do the number, you will find that this is 438 into 10 raised to 4 megawatt hour. Now let us see, it is also been told that let us calculate this in million units. Million units is million kilowatt hour. 1 megawatt hour is 10 raised to 3 kilowatt hour. So we are talking of million units, means 10 raised to 6. So then this is going to be equal to 4380 into 10 raised to 6 million kilowatt hour, also known as an MU. And you will find in many of the reports, all the electricity data is given in MUs, which is this. Sometimes you will find in the larger scale reports that instead of million units, we also talk in terms of billion units. So if this was billion units, this would be 4.38 billion kilowatt hour. Okay. So we did that first part. Now we want to see, you see, we have 9% auxiliary consumption. So this is the gross power output. If it is operating continuously, it is the maximum. We have a plant load factor of 80%. So the plant load factor PLF is 0.8. This will be the actual generation by maximum possible generation. So the actual generation is this should be 4380 million kilowatt hour, 4380 MU. This is 4380 MUs. Okay. And so, the actual generation is 0.8 into 4380 million units, which is, you can multiply it and you will get 3504 MUs. Now, this is the gross generation, gross actual generation. If you want to convert this into gigajoules, this will be now 1. If we look at this, this is 3504 into 10 raised to 6 kilowatt hours. 1 kilowatt hour is 3600 kilojoules. This is in kilojoules, and if we are multiplying, getting this in gigajoules, we have to divide this by, remember gigajoule is 10 raised to 9. So, this is so many gigajoules, and so this is the kind of calculation. Actually, we can, even the number is quite high. So, we can, instead of gigajoules, we can put this in terms of terajoules, divide it by another 10 raised to 6, and you will see that you get an answer of 12,600 126144 terajoules. You can check this number. Okay. Now, let us look at, this was the gross generation. We were talking in terms of the auxiliary consumption. So, if we look at a power plant, we have an input and we have a gross generation. This gross generation is 3504 MUs, out of which we have an auxiliary consumption A being used, and this net which we get is 3504 minus A. So, let us calculate. We are told that 9% is the auxiliary consumption, which means A divided by the net output, which is 3504 minus A, is equal to 9 by 100. And when you calculate this, you will find that A turns out to be 346.5 MUs. So, the other thing that we have to calculate, we have to calculate the energy input in terms of input energy and the annual amount of coal used. So, if you look at the input energy, we already calculated that the output is 12,6144 into 10 raised to 12 joules or 10 raised to 9 kilojoules, and the energy input will be this. This is the total output. This has to be divided by the efficiency. So, when you calculate this, you will find that this comes to 33,196 terajoule. It is a large number. It is a 500 megawatt plant, almost operating at its full load continuously for a year. So, let us see now what does this mean in terms of the amount of coal used. So, this energy is supplied by the coal. So, we will need to know how much is the amount of energy per unit of coal, and if you see, we are talking of a calorific value of 4500 kilocalories per kg into 4.18. So, this is so many kilojoules per kg of coal, which is 18,810 kilojoules per kg. Okay. So, what we need to do is we take this number that we have, the energy input that we are providing 33,196 into 10 raised to 9 kilojoules divided by 18,810. This is now kg of coal per year. That's a very, kg is a small unit, so let's make it into tons. So we divide it by 10 raised to 3, and let's see how many million tons. So we will divide it again by 10 raised to 6. So this is now million tons of coal per year. Okay. So then when you look at this, if you divide this, you will get 1.76 million tons of coal per year. We could also divide the amount of coal per unit of electricity that we are generating. Again, we can decide whether it's per gross or net, and when you do that, you find that we are using about 0.5 kg of coal per kilowatt hour. We will come back to this when we talk about the environment and other things, but here this was to just show you one simple calculation when we think in terms of energy and power, and we look at a power plant. Let's go back to our main topic, and using this we can actually build up a total the energy balance equation. Remember, we were talking in terms of in exajoules for India. You will find that the largest chunk of our energy supply comes from coal, and we get a reasonable amount of coal in terms of imports. In terms of oil, also is a major chunk of our energy supply. In the oil, the bulk of the oil is coming from imports. So if you look at the total primary energy supply of 47 exajoules, you will find that this then goes, and we can see a large chunk of the energy is going to the power sector. And then in the power sector, there are conversion losses and transmission and distribution and auxiliary losses. And then you have the electricity, which is going to different sectors. One of the major sectors is the industrial sector for electricity, and then is the residential sector, and then the rest, the commercial. And we have a reasonable amount of biomass which is being used in our energy supply. Most of it is being used in the traditionally in the residential sector for cooking with very low efficiency. So this is like a Sankey diagram which gives you an sort of overall idea of the energy situation in the country. Let's also do a simple calculation of India versus the world. We have a population of about 1.3 billion as compared to the world's 7.4 billion, and we are one of the largest countries in the world. You will see that on a per person basis, the GDP is about a little less than half of the world average, and this is done on a purchasing power parity basis. Later on in this course, we will talk about market exchange rate and purchasing power parity. If we look at the energy inputs, we can see the primary energy used is 36 exajoules, and for the world it is about 576 exajoules. And the energy used per person, again, we on an average, the energy used per person is significantly lower than the world average, maybe about a third of that. And similarly, if you look at the electricity used, 920 kilowatt hour per person per year as compared to 3000. This obviously means that on a per capita basis, our CO2 emissions are significantly lower than the world average. CO2 per unit of GDP is of course slightly higher, and we will come back to this when we talk about the Kaya identity and other factors. So when we look at different energy systems, there are many different pathways for end users. So you can look at, we talked about the energy flow diagram, and when we talk about the energy flow diagram, we are looking at different primary energy sources, whether it is solar, biomass, wind, small hydro, geothermal, grid electricity, and many of these can come into creating electricity, and then that goes into the different kinds of end uses like space cooling, space heating, water heating, cooking, lighting, and there are many different ways in which we can configure energy systems. So, with this, if we look at the overall summing up of what we have discussed today, we talked about an energy flow diagram, and we saw how we move from primary to secondary and to the final energy, to the energy end use. We then took that concept to create an energy balance diagram for a region. We looked at what factors affect the overall energy use. We looked at different units of power and energy and their conversion. We talked about a 500 megawatt power plant and did a simple calculation. If you look at the energy use pattern, we are talking of exponential unbounded growth, and that itself may not be sustainable, and that is the issue that we will talk about when we talk about energy and environment. There is a disparity between developed and developing countries, and this again is something which we will touch upon in the course when we talk in terms of inequality, measures of inequality, and see how to aggregate and look at inequality and their impacts, both in terms of income as well as in terms of energy. Drawing up aggregate energy balances, we talked about a level of aggregation which is basically for the country as a whole or the world as a whole, and we are talking of physical and energy units. The goal with what we have done today and with the references, you can develop an energy balance for a region, and we would encourage you to look at one country and look at an energy balance and look at the trends of that energy balance in that country, and this will help you get some insights on the energy systems for that country. So, the question that I leave you with is, what are the drivers for energy systems? So, we saw that population is a driver, the income and the increase, the affluence is a driver for energy systems. In addition to this, there are other drivers, and we will see that the environment is one of the major drivers for energy systems, and that will be the next theme that we talk about. In this course, we will look at the energy systems, we will look at the resources for energy supply, we will look at how to allocate them optimally, and we will look at economics, and we will look at environment. So, we will basically blend energy, resources, economics and environment to get a complete perspective and give you the tools and techniques for you to be able to analyze different decisions in the energy sector. These are some of the references which we have used, and I would encourage you to look at the global energy assessment. The first chapter provides the basics, and that will be those will give you a lot of the inputs that will be required later on in the course. There are also many different sources, and that is the International Energy Agency and the World Energy Outlook, where you will have a large number of numbers and scenarios, but we would like you to be able to go behind these numbers and to be able to do the analysis so that you can understand what is happening in the system. So, with this we will conclude this lecture. Thank you.